This presentation is over skeletal growth and repair. We're going to talk a little bit about the development of bone and how bones repair when they are fractured or damaged. So, let's take a look first at the formation of the human skeleton. Now, in embryos, the skeleton is made of hyaline cartilage. Hyaline cartilage is the precursor for all the long bones. During the development, most of this cartilage is replaced by bone, although there still remains cartilage in a couple of areas in the adult, which include the bridge of the nose, parts of ribs, and in joints. Specifically on the ends of the long bones, we have hyaline cartilage, which acts something like the Teflon coating, I guess, in your skillet. It allows a smooth sliding of the joints across one another, and because there's no blood supply, there's no bleeding in the joint, there's no pain. Now, bone growth, this process of converting hyaline cartilage into bone, is known as ossification. And there are a couple of places where we keep hyaline cartilage, like I said, in the ends of long bones, but in developing bones, we have this area that's known as the epiphyseal plate, which will allow for the lengthwise growth of long bones during childhood. And we saw an example of that in a previous discussion. New cartilage is continuously formed at the epiphyseal plate. It is formed on one side, while the older cartilage near the diaphysis of the bone is ossified. As the cartilage gets broken down, the cartilage then gets digested away, opening up this cavity, the medullary cavity, and bone replaces this cartilage through that ossification process. Now, bones do this all through growth. Actually, bones remodel all through life, depending on stress factors that are put on it. So bones are remodeled in response to a couple of factors then. Blood calcium levels, that's an important one. We need calcium in our bodies for the proper function of the muscular system, the nervous system, for blood to clot. And in the absence of the proper levels of calcium, what will happen is we will take calcium out of bone. Additionally, there is a buffer system that works in our bodies to balance our pH, and we have lots of different buffers, but one of them is a calcium carbonate system. And as a result, if you have a lot of acids in your diet, you can break down bone. Studies have shown that for women, drinking just one 12-ounce cola a week will alter the calcium content of your bones. Now, aside from growing in length, bones also have to grow in thickness to support the weight that they're carrying. This is called appositional growth, and this continues after bones stop growing in length in response to things like muscle pull. And as you can see, remodeling occurs as a product of the pull of gravity and muscles on the skeleton. So muscle pull, the stronger the muscle pull, the more weight you're moving, the heavier exercises that you're doing, the more mass your muscles will develop. So one way to build muscle mass is physical activity. Hormones also impact muscle growth and density. Estrogen helps maintain bone mass in women up through menopause, and after that, bone mass starts to decrease. There's human growth hormone, which causes the deposition of bone. And in men, testosterone increases bone mass. There are other factors as well, but those are the critical ones. Now, in terms of a developing bone, if we were looking at, we talked about how the hyaline cartilage is there, and in looking at the embryo, we have a model of the bone that's made out of this hyaline cartilage. Now, hyaline cartilage doesn't have a blood supply. As a result, it has to absorb nutrients through diffusion. And as time goes by and the cartilage gets larger, nutrients cannot diffuse to the middle of the bone. And those cells in the middle start to die off. When they die off, they release chemical compounds which the body goes in and tries to clean up. And so we get this infiltration of blood vessels. They go in there, and those blood vessels carry along with them a cell called osteoblasts, which build bone. So we end up cleaning out the dead hyaline cartilage and replacing it with bone. And there are usually several growth centers. We have one in the center of the bone, if we're talking about a long bone, which is the diaphysis. And then we have them at the end, which are the epiphysis. As the bone grows, what we end up with is largely a bony structure, but you see we have hyaline cartilage between the epiphysis and the diaphysis, and this is the area where bone growth can occur. That is our epiphyseal plate, and you can see that we have hyaline cartilage on the ends of the long bones, which allow for bones to slide across one another inside of a synovial joint. The pattern of growth that we see is that old cartilage, here's our epiphyseal plate, the old cartilage gets dissolved, new cartilage gets built, and over time we get this extension in length. Now, one thing that happens is bone growth will eventually outstrip cartilage growth. So it's kind of a race, and we can speed up cartilage growth if we were to give someone growth hormone. So a child that might be particularly small, if they still have this epiphyseal plate, we can give them a hormone which will increase their height. We can also see that certain hormones will shut down cartilage growth. In fact, estrogen shuts down the growth of cartilage, which is one of the reasons why women's bones, women's body structure is smaller than men's, is because when puberty kicks in for them, bone structure stops, or bone growth tends to, well, it does stop eventually. In men, testosterone actually enhances bone growth for a period of time, and so we tend to be larger, more bulky. Our body proportions are a little bit different. Now, there are a number of cells involved in the growth and maintenance of bone. We have osteocytes, and these are cells that are trapped in the lacunae located between the lamellae. What osteocytes are, well, they used to be osteoblasts. They used to be bone-forming cells, but in the process of building the bone, they've actually encircled themselves. They've kind of walled themselves in. So now they're more of a bone maintenance. Osteoblasts are bone-forming cells, and I don't know of a good mnemonic for that other than B for build, because blasts build. I know that's kind of counterintuitive for me because the word blast makes me think of destroying things. But osteoclasts, these are bone-destroying cells. You can think C for cut, something like that, but they break down the bone matrix. They remodel, and they assist in remodeling the bone. Depending on the stressors, we can, or our need for calcium. If there's not enough calcium in the bloodstream, the osteoclasts will start to break down the bone levels. These cells, actually the osteoclasts, are regulated by a couple of hormones. There is parathyroid hormone from the parathyroid and calcitonin, which is released from the thyroid gland. And these regulate whether we are depositing calcium into the bone or whether we are removing it. Bone remodeling as a whole is performed by both. The osteoblasts take away, the osteoblasts build bone, osteoclasts take away bone. Now, a situation where we can see this activity kind of ramped up to a heightened level is when we have a bony fracture. And just for some definitions here, a fracture is a break in bone, and there are two types. There's a simple fracture where we have a broken bone that does not protrude through the skin. It's not exposed. That's the most desirable situation. once a bone is protruding through the skin, we have a compound fracture, and it is a much more complicated situation to repair that. The inside of the human body is sterile. Once we get outside of the body, we have a non-sterile situation. We have bone that is going to die off. We have all sorts of additional problems with reapproximating the bone. Now, this process of reapproximating bone is called reduction. And why it's called that, I don't know, but we end up realigning the bones appropriately. In a simple fracture, we can usually manipulate the bones, unless we've got a crushed bone, and realign them just fine. If we had a open fracture, we're probably talking about a surgical reduction of some sort. Sometimes we can just line these up. Sometimes we have to put plates in. It depends on the severity of the fracture. But either way, we ultimately have to immobilize the bone to allow healing to occur. We have to allow these osteoblasts and osteoclasts to come in and repair this damage. Now, we're going to talk about how that repair occurs in a minute, but first I want to tell you a little bit about some common fracture types. And there are characteristics to each and situations where these would occur. This table is in your textbook. The first fracture is comminuted, and this is where the bone breaks into a lot of fragments. It doesn't just break in one spot. It pretty much shatters. This is common in older people whose bones are very brittle. This is the kind of break, too, where you might have someone hit with a baseball bat, a large, blunt instrument that spreads stress across the entire bone. Compression fracture, the bone is crushed. Kind of similar to comminuted, but in this case we have squeezing forces that break it. It doesn't shatter so much as it breaks into a lot of different chunks because of the compressive forces involved. We also see this in porous bones like osteoporosis and in older people. Now, depressed fracture, you have to have a hollow space, and one common hollow space is the skull. We also have sinus cavities, but this is the area where you're going to see a depressed fracture. A broken bone portion is pushed inward. It may impinge on the brain. If it's in a sinus cavity, it may not. But this is typical of a skull fracture. We have impacted, and this is where bone ends are forced into each other. What we see here is usually someone trying to break a fall or brace themselves in some way. So if we were to catch ourselves from a fall, we might get a compression fracture. If I were driving down the highway and stiff-armed my steering wheel just before a wreck, I would probably have some sort of compression fracture in the arm. If the parachute didn't open soon enough, I might have a impacted fracture when I landed. Now, spiral fractures, this is a ragged, twisted break, and we do see this in sports injuries. People who ski and are doing moguls going down a hill, and they just twist wrong. That can happen all the time. This is also an injury that can be indicative of child abuse, and that is something to be aware of. A parent grabs a child by the arm and hoists it up into the air. Some, actually, fathers will grab an arm and twist it as a form of punishment. So when someone sees a spiral fracture in a child, there are some alarms that tend to go off. You start to wonder, how did that happen? If a parent were to say they fell down the stairs, that's not the type of fracture you're going to get from a fall down the stairs. You might get an impacted, you might get a comminuted. You're not going to get a spiral fracture from a fall. On the other hand, if they said the child was swinging and they had their arms wrapped around the rope or the chain, and when they decided to jump out of the swing, their arm got caught. That is a valid history, and in a situation like that, you would actually see the marks on the arm. Now, the green stick fracture, the bone doesn't break completely. It is spring, sunny weather, and there are plants all about, and they have new growth, and they have lots of fibers in them. And we have lots of fibers in our bone. We have collagen fibers that run through, and they act like the reinforcing steel in steel reinforced concrete, so that the calcium salts can break, cracks can propagate, but the fibers are still holding everything in place. The periosteum that surrounds bone can hold it in place. We see this in children quite often. As children, their bones are still developing. They have a high collagen fiber content relative to their to the content of the calcium salts. This can happen in the elderly as well. It can happen all through life, but it is really common in children. Now, at this point, I'm going to stop. We're going to pick up on this discussion again with slide 10 at a different presentation, and we'll begin with the repair of bony fractures.